Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll discuss the thermal stresses induced in a composite bar due to temperature change when they are connected parallelly. Now let us consider a composite bar connected parallelly. So initially they are of length L. They are of two different materials, material 1 and material 2, and they are rigidly fixed at one end. They are also joined together, and no separate deformations is permitted. They are rigidly bonded together. To demonstrate, I have fixed one end. Otherwise, composite bar, if they are connected and their individual expansion or contractions are not permitted, then it can be considered as a composite bar connected parallelly. Now in this case, I'll fix at one end, and the bar is allowed to expand in the other direction when the temperature changes. The bar is allowed to expand or contract when the temperature changes. Now assume that material 1 is having higher coefficient of linear expansion than material 2. So when it is heated and if they are separate bars, it will expand by an amount alpha 1 L delta T. Okay. And material 2, again, if it is free to expand and if it's heated, it will expand by an amount alpha 2 L delta T. Is having less coefficient of linear expansion compared to material 1. So material 1 natural expansion due to the temperature changes alpha 1 L delta T, which is greater than the expansion that would have produced by material 2, which is only alpha 2 L delta T. So this is the expansion if they are free to expand and if they are separate bars. But when it is a composite bar, this free expansion, natural expansion, are not permitted. They are joined together. They are not allowed to independently expand or contract. Contraction also, if the material is cooled, both will try to contract. So in this case, free expansion is not allowed, even though the material 1 can expand alpha 1 L delta T, and material 2 only trying to expand only alpha 2 L delta T. These individual expansions are not allowed when they are connected. Now both will expand, but there will be a compromise between these values. There will be a compromise, and since material 1 is trying to expand more than material 2, material 1 will pull material 2 beyond its natural expansion. So material 1, since it is trying to expand more, it will pull the material 2 beyond its natural expansion, which is only alpha 2 L delta T. So it will be pulling, the material 1 will be pulling the material 2 along with it, because it is expanding more. So it will exert a tensile force on material 2 and pull it beyond its natural expansion. Okay, so this del A which I shown is the expansion allowed. Both will expand when they are connected parallelly. When they are in a composite bar, both will have a compromise and expand by del A. That is the allowed expansion in both the materials when they are connected. So material 2 will expand more because of the pull exerted by 1, whereas material 1 cannot expand to its full, because this is exerting an opposite force, because it is expanding only less, and it will exert a force towards left, preventing this free expansion. So there will be a compressive force on material 1 exerted by 2. 2 will exert a compressive force on 1 and reduce its expansion to del A. So in both the materials, there will be a difference from the natural expansion. If it is free, material 1 will expand by alpha 1 L delta T, so much. But that is not allowed because this is not permitting that, it will exert a compressive force. And whereas material 2, its natural expansion is only alpha 2L delta T, it is pulled beyond its natural expansion by material 1. So it is subjected to tensile force. So there is a compressive force induced in 1 and tensile force induced in 2. Since there is no external force acting, these forces, net forces, compressive force and tensile force, that is the only forces induced because of this temperature change. So this summation of forces must be equal to 0. So this compressive force and tensile force both are acting in opposite directions. The summation should be 0, or this compressive force and tensile force magnitudes must be equal. So compressive force induced in bar 1 has to be equal to the tensile force induced in bar 2. So this is when material 1 is having higher coefficient of linear expansion, or whichever material is having higher coefficient of linear expansion, that will be subjected to compressive force when it is heated, and the other material will be subjected to tensile force. So it is material 1 is subjected to a compressive force exerted by 2 on it to reduce its free expansion, and material 2 will be subjected to a tensile force to increase its expansion beyond its natural expansion. So these compressive force induced in 1, tensile force induced in 2 are equal. So compressive force induced in bar 1 and tensile force induced in bar 2 are equal. And if you assume a stress of sigma 1 in bar 1 and area of cross section of bar 1 is A1, sigma 1 A1 will give the force in bar 1, compressive force in bar 1, and tensile force in bar 2 is stress induced in the bar 2 into area. So sigma 1 A1 is equal to sigma 2 A2. This is only magnitudes I equated. They are of opposite sign, but magnitudes are going to be equal. Magnitude of compressive force induced in 1 is equal to the magnitude of tensile force induced in bar 2. So sigma 1 A1 is equal to sigma 2 A2. So you can say sigma 1 is A2 by A1 into sigma 2. So its area ratio, sigma 1 is A2 by A1 into sigma 2. So it all depends on areas. Okay, so A2 is more and A1 is less, then you get this factor higher, and stress induced in bar 1 will be higher. Both are of equal area, stress induced will be equal. Whichever material is having a lesser area, that will be subjected to higher stress, but one is subjected to compressive stress, other one is subjected to tensile stress. So this is different from a single material. When it's single material, when it is heated and constrained, that will be subjected to only compressive stress. But in a composite bar, when it is heated, the material which is having less coefficient of linear expansion will be subjected to tensile stress. Okay, so tensile and compressive stresses are possible in a composite bar. So this is while heating. If it is cooled, if the temperature is reduced, now what happens? The material 1 will try to contract more, whereas material 2 will contract less. So the material 2 will not allow this free contraction, because material 1 is trying to contract more, material 2 is contracting less, free contraction is less. So this material 2 will exert a pull, tensile force will be exerted on 1, and similarly material 1 will exert compressive force on 2 to increase its contraction. Okay. There will be a compromise and contraction will be somewhere in between. So material 1 is trying to contract more, so this has to exert a pull on 1, and in turn 1 will exert a compressive force on 2, which will increase its contraction of 2. So there will be a compromise, and there will be equal contraction in both the materials when they are in a composite bar, when they are connected. So in case of cooling, the material which is having higher coefficient of linear expansion will be subjected to tensile stress, and other material will be subjected to compressive stress. So in a composite bar, the material which is having higher coefficient of linear expansion will be subjected to compressive stress when it is heated and tensile stress when it is cooled. The other material will be subjected to opposite stresses. Now we have already framed an equation for the relationship between stresses. The stress in the materials are related by area ratio. Now we will get another relation by checking the expansion of these curves. Now let us say del A is the expansion allowed in both the materials. So they are expanding only by del A. Now del A in this bar 1, del A how you get? Alpha 1 L delta T, that is a free expansion, and after this let us assume that it is allowed to expand freely. Okay, initially it is allowed to expand freely, then bar 2 is exerting a compressive force and reducing its expansion. Okay, so it is expanded freely, so it will expand by alpha 1 L delta T. Then bar 2 is exerting a compressive force and reducing its expansion to del A. So to get del A, you can say the free expansion alpha 1 L delta T minus change in length due to that stress will give the permitted expansion or allowed expansion. So the alpha 1 L delta T minus sigma 1 by E1 into L, that is strain into the length of the bar, will give the change in length in due to that compressive force. So this compressive force is inducing a change in length, and that change in length you can calculate as strain multiplied by length. Sigma 1 by E1 is a strain into length of the bar will give the change in length caused by that stress. So free expansion minus change in length due to that stress will give the permitted expansion or allowed expansion. So alpha 1 L delta T minus sigma 1 by E1 L, it is nothing but a del A permitted expansion in both the materials. Now bar 2, it is only expanding by alpha 2 L delta T. Okay, now that is a free expansion. Now material 1 is pulling it, and that pull or tensile stress is expanding it further. So the elongation produced by the tensile stress, if you add to this alpha 2L delta T, you will get the del A. So this del A is also equal to alpha 2L delta T, so much, plus the change in length induced due to the tensile force acting on it. So that is change in length is strain into length. Strain induced is sigma 2 by E2 into length. So that will give the change in length due to that tensile force. So you will get this plus change in length due to the tensile force, that will give del A. So both can be equated. Now L1 and L2 are same. This is L1 and L2, but L1 is equal to L2. L can be cancelled because every term has L, so L can be cancelled. So the same equation I have written after cancelling the L common factor, and now I am taking that stress terms in one side. Sigma 1 by E1 plus sigma 2 by E2, okay, is equal to alpha 1 delta T minus alpha 2 delta T. So sigma 1 by E1 plus sigma 2 by E2 is equal to alpha 1 minus alpha 2 into delta T, and that is the second equation. So you have another relation for the stress induced in the bar. So if you know the Young's modulus of the materials and the coefficient of linear expansion and temperature change and the areas, you can solve for the stresses induced in both the materials. Because we have one more relation, sigma 1 is equal to A2 by A1 into sigma 2. So there you get a relationship, provided you know the areas of cross section of both the materials, you will get a relationship between sigma 1 and sigma 2, and here you have another relation between sigma 1 and sigma 2. So two equations, and you have two unknowns, that is two unknown stresses. You can solve stresses induced in both the bars, and also you can find out the forces induced in. Once you get the stresses, you can find out the forces induced in the bars. So stresses will be induced in the composite bar due to this temperature change. And in a composite bar, when they are heated, the material which is having higher coefficient of linear expansion will be subjected to a compressive stress, and other material will be subjected to tensile stress. Whereas when it is cooled, the material which is having higher coefficient of linear expansion will be subjected to tensile stress, and the other will be subjected to compressive stress. You can take like this: the material which is having higher coefficient of linear expansion will be always trying to expand more when it is heated, then the other one has to exert a compressive force on it. The other material will have opposite stress. Whereas when it is cooled, the material which is having higher coefficient of linear expansion will try to contract more, then the other material has to exert a pull or tensile force to reduce this contraction, and the other material will be subjected to compressive force. That's all for today. Thank you for watching.